Okay, so as you can see here, there's an incoming car which is not in the right lane, so it is kind of going in the direction of the Waymo car, and it is about to crash. So this is a very close call. And what the car managed to do is that, oh, it took it slow. Well, you can see what the Waymo car managed to do is that it managed to swerve around. And one of the most impressive thing that I think people have been talking about this video is that it actually climbs a bit on the sidewalk or whatever the plan is, in order to avoid the incoming traffic. And as a person who actually worked at a autonomous car company in the past, I know that for most of the algorithm that they define in the companies, they place a very heavy penalty on the car actually going off the road, right? So if you go off the road, you are very likely to crash somewhere. So it has to have a very high penalty. But for this example, right, you can see that going off the road is actually the only way that you can avoid the very tragic accident. And so that brings up a very important question. So how should you tune the rewards for each of the states? So should you have a very big infinite, maybe close to negative infinity reward for going off-road? Or do you have a even bigger, maybe -2 negative infinity of um having a car crash or something. So it's very difficult to define what a reward is for each of the states. And this is only a very simple, I think this is a very simple case of traffic maneuver where you only be on the straight road and you only have two side way, you don't have an intersection and you only have one incoming car. But for other instances, I think it might be even more complicated. So defining a reward for the training environment is not simple. And so in some case, for example, like in chess or in Atari or maybe in robotics, we often don't know the best action is. If you're a chess player, then there are a gazillion of possible moves that you can take, and you want the agent to be able to explore new ways. Maybe you sacrifice a bishop or a queen or something, but eventually you win the game. But for some other cases, like you are a driver or you are a surgeon, then there are not many ways you can do to get a good outcome. You cannot sacrifice a kidney to save the other one or something. You have to be optimal. So in such case, how do we choose rewards for these high stakes situations? It's a very open questions, and imitation learning is one of the way to pick the rewards. And the idea of imitation learning is that instead of the researchers, the computer scientists who literally doesn't have much experience with driving or maybe with medical, we let the experts do the task, which is demonstrate the agent how to drive or how to do surgery or how to treat patients and all of that. And then after the artificial intelligence sees a demonstration, they will learn the reward functions, which will be applied to other circumstances. So in the picture, you will see that there is a person is demonstrating a driving on a highway to a computer. And this is excerpt from a paper from 2004 by Peter Abil and Andrew Ng. And this is one of the very kind of first and pioneering papers in terms of demonstrating for imitation learning on a simulated environment. So the idea of imitation learning is that you have the expert to provide a set of demonstration trajectories, which is basically a set of sequence of steps and actions. And later in this lecture, I have also designed an environment so that you can run your code on and also train a self-driving environment. Now, when is imitation learning more useful? Well, as I have demonstrated in the previous examples, it is useful when it's easier for the expert to demonstrate rather than for us to specify a reward that would generate such a behavior. So it's easier to just avoid the car than uh, than to design a reward that maybe prioritize going off-road than avoiding the car. And it's maybe in some circumstances you don't even want to be very discreet about what you do. Maybe not even go off-road, maybe not even go sky, maybe just stop or something like that. One of the most important, and I think everybody should know when they learn about imitation learning, the algorithm is called Dagger. So Dagger stands for the dataset aggregation. Um, have anybody in the room heard about Dagger before? Okay, I guess not. Um, okay, so basically, you can imagine that there's a uh, retarded Bojack here. He's very dumb. He doesn't know what to do, but he just recently seen the environment and he has to ask an expert, what should I do? What should I do in this situation? And and maybe uh, the expert would say, okay, slow down, turn a bit left. And the Wojak would say, okay, I will slow down, I'll turn left. Now I get to a new state. What should I do? And this conversation goes on, and that is how we collect the trajectory of the expert. And after each of the iteration, each of the trajectory you collect, the Wojak will get smarter. It will be able to make more informed decisions. Maybe after the first information, it might not be able to slow down enough or turn left enough, but after a few iterations, it will be able to. And so after every time the data is collected, you do supervised training on that data set and you repeat the entire process of querying and rolling out the trajectory. So this is the pseudocode of the Dagger algorithm. Even though I know that this is intimidating to some of you, I do think that this is one of the easier and more memorable way uh, to approach this algorithm. So okay, so let's go through this line by line. First, you want to initialize an empty data set. So this data set is the data set of all of the observations that you are ever going to see in this algorithm. And you initially have a policy that is random. So for each of the step, uh, each of the iteration, you are going to sample the trajectories, which basically is the same as having the Wojak and the expert dialoguing with each other t times. And after that, you collect the data set, which is basically the pairs of the questions and the answers. And then you combine that to the data set, and then you train the new policy on that new data set. And after that, you have an evaluation, which I believe is covered in the reinforcement learning lectures. So you can go back and watch it. I think it's very helpful. Okay, I think it's simple enough, right? So as I promised, I have designed a environment for you guys to actually train something for yourself. And it's very quick and it's fun. So let's do it. So here's the environment setup instruction. You can follow it. Please let me know if you have any question. Oh, and by the way, I think this is the first time we don't use the Google Colab. So if anyone wants to just have a repository in the future, then we might need to figure out something else. Let me see if there's a way to that I can still show this on the screen, but then I can put up the code in another one. I think the most important thing for anyone who wants to install this is that you have to separate the thing into a virtual environment because some of the dependencies are quite old. I have to take it from another repository, but as long as you get that done, then installing the requirements will be pretty easy. Um, right. So, okay. So let's see. So this is the screen for my code. What you can, okay, so actually I first want to show you the code. So basically here you are going to create an environment and you are going to be training by actually driving the car. And after a certain amount of time, I think I set it to like 500 time steps, then it's going to stop. You're going to save the progress, and then it's going to uh, show you the result. So let's try it. Ah, but have to. Oh, actually, am I sharing? Yeah, should skip scripts. It should be the right. Okay, okay, it runs. Okay, so what you can see is that the you oh actually I am driving the car right now. So what you can see is that you can actually manipulate the racing car. This is created not by myself, but by a API by OpenAI called Gym. So you can create a lot of training environments in with this package library, whatever you want to call it. And so this is one of them. Beside this car racing, you're gonna have Cartpole, which is an also very popular Hello World environment for reinforcement learning. And oh, what's going on? Uh, and and then there are also going to be other like humanoids or stickman working or um, I think another popular environment is uh, a crab or crawling something. So it's interesting. You will see them used repeatedly in all of the reinforcement learning papers. Okay. Uh okay, now that we have the policy, we can try to play some of them. So I have prepared a few policy like in advance. Takes a while because I'm not a driver. So let's see. Uh, test agent, I, and then let's see which one do I want? E, and then let's play the Model 3 because it's one of the midpoint, and I don't know how it goes. Okay, now it runs. Let's see how well it learned. Oh, okay. Veered off the road quite quickly. I didn't expect that, probably because I had veer off the road very quickly in the very first iteration. And also because I'm pretty bad driver. But you can see the model kind of learns from both the experience and the mistake that you are going to make. And I really encourage you to actually try to run this code for yourself because you're going to see that it will learn very quickly as long as you provide a very good demonstration. And in addition to that, you can also configure how long you want to train the car for. So for each iteration, how much data you can collect before the training actually happens. Okay, so this is a very bad model. I'm not going to play it anymore because there's no point in showing that. Let's see if the model 6 is any better. I think it also runs slower because we are connecting to too many screens. But actually, when I run it offline, then it is like a race car. Oh, okay. Oh, so this is the much better one. I think this one is the result of one of my more consistent driving, if I was not mistaken. Well, but yeah, as you can see, the for the numbers that are on the side, that is how far you have gotten with the car, and the blue is the acceleration. So the car is going at full speed. The green and the left are how much you are turning left and right. So if you are turning more left, if the wheel is like turning left, then you see more green on the side, and then if the wheel is more like to the right, then you see more red. Yeah. So uh, sometimes you have to have both to keep balance of the car. And yeah, I think for the past 2 minutes, the car hasn't been gone off the road anyway. So there are many tweaks you can do to this. Maybe you can add one or two more cars. I think that is also customizable. Make it steer away from the traffic, make it learn from um, you know, different terrains. This is learned by uh, taking the 96 by 96 image of this simulation, and then you can pass it to um, grayscale. So the terrain should not be really different, but of course you can still try to have different colors of the side, or maybe have different colors of the road, and try it out. Okay. Uh, and yes, of course, you have the link to the repository. So if you would like to try it out, then please feel free to do so. Have any question, please let me know. Um, okay. Uh, so moving on from that demonstration, I want to talk about another thing, which is ambiguity in imitation learning. Uh, okay, so in driving a car, for example, it's very complicated reward model. Uh, but even in the simpler reward models, given that the expert demonstration is optimal, then we still have the question of, is the learn reward model unique? And for example, let's say if the optimal strategy is just to stand still, right? Then you're going to get 100, for example, reward for standing still. But then you can get 5 reward for going left, 4 reward for going right, or maybe 6 for going left, 5 for going right. So the idea is that there are many different reward models, not a unique one, that can fit the same limited expert demonstration. Right? If you are studying math, then you probably know that if you have a finite number of points on a plane on the graph, then you can fit a single line through all of them, right? By Lagrange interpolation. And so this is pretty much the same thing. And researchers for the past, I believe, almost 2 decades have tried to tackle this with many different approaches, which of the 2 papers are the maximum entropy inverse reinforcement learning, which was introduced all the way back in 2008, and a more recent one, 8 years ago, the generative adversarial imitation learning in 2016. We are not going to go into depth for both of these papers. I will slightly mention the first paper in the later slides, but I would also highly encourage all of you to be looking them up and maybe try to figure out some of the key ideas yourself. Right. So, okay, we are finally to the second part of this lecture, which is reinforcement learning from human feedback. Okay, some of you at this point might ask the question, okay, isn't in imitation learning already human feedback, right? Because after all, what we did was that we take the instructions from a human, maybe driver, maybe surgeon, maybe, I don't know, maybe a farmer or whoever. And then you try to feed that into the model and then you make it learn from the demonstration. So isn't that already human feedback? But we can come back like 2 or 3 slides to here, and we can see that, okay, just the demonstration is not enough, because if we have the demonstration, then what it has to do is that it can output many reward models, and as the result of different rewards model, then it can make different policies and it can return different course of actions. And so we want to always choose the most optimal, and not only optimal, but also most aligned with our common sense, right? For example, yes, you can take the shortcut on the road, but you also want to be obeying the law, for example. So you want to have a supervisor who is also human to be able to choose between the very, very diverse course of reward and policies that your imitation learning algorithm can generate, and then you want to choose the optimal output. And so that's the idea of reinforcement learning from human feedback, which you might already see if you use ChatGPT or Claude or other NLP models nowadays. They have the options for you. They generate multiple outputs, and then they ask you to choose, okay, do you like the first response or the second response better? And that output is actually going to be fed into one of these preference learning models. Okay, so maybe we let user choose, as in the case of ChatGPT, and if so, then how do we select the winner from the many, many, many options that we give the users? So maybe for the same questions, ChatGPT will give me 2 answers, but then for you, it will give you 2 more answers. And for Ryan and for other board members, they're gonna give you a few more options to choose. And so we need to select from a very big pool of candidates which one is the winner. And so there are a few type of ways that we can select the winner. One of them is Condorcet winner, Copeland, and border winner. What the idea is that for Condorcet, the idea is that if a candidate has the higher wins like every other one candidates, then it's the winner. For the Copeland winner, it's if a candidate has the highest win rate among of all the candidates, then it's the winner, etc. The list can go on, and you can define the score for each of the candidates in a very different way, and it's also dependent on the uh, the model that you are trying to learn. However, today I want to talk about one way that we can choose the winner, which is we want to choose them probabilistically, which I believe is also kind of true for the other candidates. Sorry, for the other algorithms of choosing the winners. But this is more generic and I think more applicable widely. Yeah. Okay. So it might be a little overwhelming to look at this algorithm here, but basically P of BI is larger than BJ. It's basically interpreted as probability that option I is preferred by someone not polled an independent user over the option J is equal to this formula. EXP here is the exponential, of course, you will know this. RBI is the score that we are currently recording of option I. RBJ is the score. However, we want to record it currently of option J. And using that, we have been able to encode the probability of BI winning over BJ as PIJ. If you look at this formula, it actually makes sense, right? Because if the score of I and the score of J is equal, then the probability is actually 1/2. So it makes sense. And if score of I is less than the score of J, then it's going to be less than 0.5 and vice versa. So it kind of works, right? But then one of the more interesting thing that we can do with this formula is that we can model it in terms of cross entropy. So this goes ways back into the very, very first chapters that we had of supervised learning. So we can take the logarithm of probability plus the logarithm of the probability that J is larger than I. And then mu here is the score factor. So you just don't want to miss out on who is winning. So basically, if you remember the original, can I annotate? No? Oh, oh, okay. Never mind. Never mind then. Okay. So if you can, let's see, is there no way I can annotate? Hmm. Okay, never mind. Sure. So if you remember the cross entropy from way back from the supervised learning, you will remember that the term mu1 here is actually replaced by the term p. So basically the entropy is p log p plus 1 minus p log of 1 minus p, right? So in essence, you replace that term here, and here you will get back to the cross entropy. Now, this is actually very relevant to the one that I showed you earlier, which is this paper, the maximum entropy inverse reinforcement learning. So the key idea here is that because you have the entropy and you can model the loss in terms of entropy. So you want the entropy to be maximized. And I know it sounds a little counterintuitive, right? Because why would you want to maximize the loss? But the idea is that if you remember the lectures on PCA, you will recognize that because in terms of knowledge that you actually gained, if a data set has a bigger variance, then you actually knows more about what is being stored inside a data set. So in the worst case, you have nothing. It's an empty data set. It's just a point. The entropy is the smallest. So you're actually making random actions. But the more knowledgeable you are, the more diverse your experience and data set has to be. So you're gonna get a bigger entropy. And that's the reason why we need maximum entropy in reinforcement learning. Okay, so that is the idea of reference learning. Um, in this very last example, I want to show a example from OpenAI, which is published, I think, in 2018, about 5 or 6 years ago. This is a stickment. You can also simulate this in OpenAI Gym, which is the API that I used to um, simulate the car racing environment that you just played on a few minutes ago. Okay, full screen. As you can see here, uh, the user is like directing the model which one is better. So right is better, now left is better. And this stick pole is trying to do a backflip, by the way. So at the end, it should be able to do a backflip. Very close. Yeah, okay, there you go. So well, I do believe that this video is kind of sped up, but I also can also see we being able to train this kind of algorithm within, I believe, not a very long time, maybe 10 minutes, maybe less, because, imitation learning and then other kind of policy gradient methods are very powerful. So that is kind of the state of the art. Kind of approach that is underlying many operations. Right now, you can see it in autonomous driving vehicles, and then you can see it in robotics, biomimetic robotics like Mini Cheetah and the Spot from Boston Dynamics and MIT are also using it to train the robots to do backflip and to say hi and to parkour and all these cool stuffs. So I do hope that this lecture is going to give you a glimpse at the tip of the iceberg of everything. And please check out the links that I attached to this lecture. And if you have any questions, please feel free to follow up with me. Thank you.